Can you see it, right? Okay. So, suppose you are given the matrix A. This is given. Matrix A is given. It's an n by n. Okay. So, lambda here is a scalar. Is a scalar, which we call the eigenvalue. Eigenvalue. And the vector x here, we call the eigenvector. Eigenvector. So this we call, in mathematics, we call it the eigenvalue problem, standard eigenvalue problem. For a given matrix A, square matrix given to you, we have to figure out what is the eigenvalue and what is the eigenvector. So the way it works is from this equation, we can move the term on the right hand side, move to the left. So it will become minus, move to the left, and equal to, you agree? Right? So you move the term on the right hand side, lambda x, you move to the left. That's why it becomes minus. Okay? And then we can factorize the x. So this becomes a minus lambda I x is equal to 0. Correct? Because you factorize the eigenvector x. So what you have left, just lambda and I. I here, we call it is the identity matrix. This is called identity matrix. Identity matrix. Alright? Identity matrix. And of course, the identity matrix, it will look like this. 1, 1, 1, blah, 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 1. Everywhere else is 0. Is that right? So, I is the identity matrix. The diagonal equal to 1. Everything else 0. Now, remember, in this eigenvalue problem, the matrix A is known, is given to you. Alright? And you have to find out the eigenvalue, and you have to find the eigenvector. So, from here, you can go to here. Is that clear, right? Now, next step. You see this one right here? This is also is a matrix. Right? A is a matrix. I is a matrix. So, this one is, you can call like A star. The whole thing here, you can give it a new name. You call it A star. And this x is equal to 0. Is that okay so far? Right? Now, last time in my previous lecture, we learned how to solve A x equal to b. Remember we learned how to solve A is equal to b using Cholesky method. Remember that? Right? Now, this one looks very similar like that form. What is the difference? The difference here is you can think the vector b on the right hand side now becomes 0. That is the difference. Right? Now, remember what is the unknown? The unknown is lambda. The unknown is lambda. And also, which is the eigenvalue. And the unknown is x, which is the eigenvector. So x is the unknown. So when you have a system of equation and the right hand side equal to 0, what is x? Of course, x is equal to what? 0. Because when x equal to 0, it will satisfy this eigenvalue problem. But we don't like it because this is called like a trivial solution. We don't want it. We don't want it. So in order to have a solution x, which is different from 0, what is the requirement? The determinant of A star has to be 0. Okay? So here I say, in order to have the solution x vector different from 0, then we require the determinant like of this matrix A star equal to 0. Okay? Now, let me give you an example. So hopefully you can understand easier. Okay, let me give you an example. So here is an example. I say given the matrix A, let's say 2, -1, -1, 1. Okay? Now I ask you, here's my question. Find the associated eigenvalue and eigenvector. So that's the question. Now, remember I said to you, you have to say, remember you said A star equal to A minus lambda I. Remember that? Right, from the previous page. So let's plug in the number. A is here. Matrix A is 2, -1, -1, 1. Right? And then minus lambda times the identity. So this becomes minus lambda in here, minus the lambda in here. Is that right? And then we require the determinant of A star to be equal to 0. Like I told you, in order to have a non-zero solution. So that means you have to take the determinant of 2 minus lambda minus 1 minus 1, 1 minus lambda equal to 0. Okay? And of course, this means this times this. 2 minus lambda times 1 minus lambda minus 1. You agree? Now, of course, this right here is the quadratic equation. So-called quadratic equation. Lambda squared. Quadratic. So you can solve to get 2 roots. Okay? So of course you can get 2 roots. Lambda 1 equal to some value. And then lambda 2 equal to some value. Okay? And these are called the eigenvalue of a matrix A. Okay? Now, how about to find out the eigenvector? See the eigenvector? We have to figure it out. So the way to do it is, you remember, we say A x equal to lambda x. Remember that? So we plug it in, the value. A is here, 2 minus 1 minus 1, 1. X is the unknown eigenvector. x is the eigenvector. So it will be like x1, x2. Now, if you let lambda equal to lambda 1, okay? So you get lambda 1, which is known. You just solve it. Times x, x1, x2. So from this system, you can solve for x1 and x2. It will be equal to some value, some value. Now, these are the component of the first eigenvector. The superscript 1 because you're talking about the first eigenvalue. So this will give you the first eigenvector associated with the first eigenvalue. And then you do the same thing similarly. Now you let lambda equal to lambda 2. Right? You go back and then you solve it again. Now you get x1, x2 with the superscript 2. So that's the way to get the so-called eigenvalue and eigenvector. Now the reason I have to review this thing is because today's lecture, it will be something related to this one. Okay? So do you have any questions so far? Okay. So you understand this thing, right? So the next thing we're talking about, go back to the last lecture. Now you remember in the last lecture I said we want to solve ax equal to b. Ax equal to b. And in the last meeting I told you that we have two big different group of methods. This one we call direct method. Direct method. The other group we call iterative method. Iterative method. Okay? Now, in the direct method, you have many other methods, such as Cholesky. Remember the Cholesky we already discussed in our lecture, right? Okay? And now this Cholesky, it is only work if the matrix A is what? Symmetric, positive, definite. So you get the Cholesky. There's another method we call LDL transpose. You use this method if the matrix A has to be symmetric, positive, definite, or negative definite, both. It could be positive, it could be negative. Then you use this method. Or you can use the so-called LU method. LU method. If the matrix A is what? Unsymmetric. Unsymmetric. Now, of course, so far I only explained the Cholesky, but these two methods is similar. Okay? All of these three methods belong to the so-called direct method. And the main thing in here is what? You have to do factorization. Remember, step 1, forward solution. Step 2, backward solution. Step 3, remember? All of those three methods require to do factorization, which is very expensive. Now today, we're going to talk about this group, today's lecture. So this group, iterative method, again we have some of them. Conjugate gradient, CG. Conjugate gradient. Conjugate gradient. This method will be apply if the matrix A is, let's say, symmetric, positive, definite. Okay? Or there's some other method like GMRES. If you do Google search, just say GMRES. Okay? Or there's another one they call biconjugate gradient. Biconjugate gradient. These methods will be applied if the matrix A is unsymmetric. Okay? Now, by the end of today's lecture, I hope I can explain to you this thing. But the idea is also very similar for this method. And by the end of today's lecture, I will also suggest you a research topic. And I hope that you have until May next year to do it. Okay? So let me focus on this thing for today. Okay? So, in order for you to understand this iterative method, conjugate gradient, so let's look at the page 414. 414. I'll show you. See, this is chapter 6 of my book. This is chapter 6 of my third book. But if you go to this one, and you go to page 414. 414. What page is this? Oh, still have a lot to go. Ah, okay, here it is. Yep, actually, take a look at page 413. 413. Take a look at page 413. So, page 413. Okay? See here, we are talking about conjugate gradient. Conjugate gradient, which is this method. Now, please remember, the conjugate gradient method will be able to help you to solve simultaneous equation A is equal to B. Now, I will give you the so-called step-by-step algorithm, which is not too difficult to understand. You just think about it. First, you have to give the initial guess of the solution. You understand? Because you want to solve, okay, the matrix A is given. You agree? B is given. And X is what you're looking for. Correct? So, in the first step, you just guess the solution. Guess. Okay? So, like for example, you just guess X0 equal to whatever the value. Because you just guess. You just guess it. So, say 1.2 minus 3.6, whatever. You just guess it. Is that clear? So, this is your guess. This means iteration 0. Iteration 0. It's because in the conjugate gradient, you just do iteratively. Okay? So, this is your guess for the solution at iteration 0. Okay. Then after that, you compute the so-called initial residual. Do you know what residual means? Residual means like error. The error. Like, suppose you are very lucky. Suppose you are very lucky. And you guess this guy. And this guy happened to be correct. It means you are very, very lucky. Now, if that is the case, then what will be the residual vector? It will be equal to a 0 vector. Am I right? Yes or no?
Yes.
Okay? But usually we are not that lucky. Alright? So the residual, what the error, is a vector. At iteration 0 is equal to this minus that. All you have to do is just bring this to the other side. Very, very simple. So you can calculate the initial gas, all right? Then you initialize another vector that called vector D at iteration 0 equal to 0, 0, 0, 0, 0 vector. And then you initialize a scalar value, rho with the subscript minus 1 equal to 1. It's just an initial. Now, you go through a do loop. How many of you here know Fortran language, by the way? Fortran, right? Doesn't matter, you know Fortran or C or C++. Basically, this is a loop, all right? So, the first time of the loop, I is equal to 1. Do you agree? Now, when I equal to 1, you want to calculate this value. Now, when I equal to 1, what is R? R0, right? When I equal to 1. R0, well, remember R0, you already computed here, okay? So this is just like to take the dot product of the two vectors. Understand? Okay, so you will calculate this number. After that, you calculate another value, beta, I minus 1, which is equal to rho I minus 1 that you got from here, divided by rho I minus 2. Now be careful. When I equal to 1, what is this guy? Rho of negative 1 that you initialize here. You see? So you can calculate beta I minus 1. After that, you calculate the vector D at iteration I mean equal to 1, equal to the vector Ri minus 1, which is right here, plus beta I minus 1, you compute it here. D0, you get it here. Is that clear? All right. Then you calculate the vector Q equal to the matrix A, which is given to you. Vector Di, you just compute it here. Then you go down, you calculate alpha I, rho I minus 1, that is here. You already know. Vector Di, you already calculate here. Qi, you already calculated. Do you understand? So you take the dot product, and then you can find out this guy. And then what does this formula say? This is the new improved solution. Now, right now, what is the value? I equal to 1, right? I equal to 1. So what does it say here? Vector x at iteration 1 equal to vector x at iteration 0, which is your initial gas. Plus alpha I, you calculate here. Di, you calculate here. So you can calculate this guy. This xi is supposed to be the improved solution. And then you calculate the new residual or the new error. Ri minus 1, which is this guy. Alpha I from here, Qi from here, so you can calculate this. And then you ask, converge or not? Right? Converge or not? Well, if it is not converge, then you have to go back. If it converge, then you stop. Is that very clear?
Yes.
Now, this is very simple. You can see in any textbook. Very simple. But the main thing about this conjugate gradient is what I told you this. Do you see anywhere in this procedure that you have to do factorization? Yes or no? In this procedure, is there anywhere you have to do factorization? No. You see that? So that is the main difference between this method, conjugate gradient, compared to the Cholesky. Because factorization, you remember, is very expensive, number one. Number two, do you remember when you do factorization, what is the bad news?
You have the fill-in terms.
Non-zero fill-in term. That means you have a lot more non-zero after you do factorization. In this procedure, you never have that problem. Why? Because you only deal with the matrix A. That means if you have in the beginning, if you have 6 non-zero, you always work with 6 non-zero. That non-zero will never increase in this procedure. So far, this conjugate gradient have a lot of good news, am I right? But what is the bad news? The bad news is, you see this is the iterative. It may take you 10,000 iterations or more. It takes a long time to convert to the correct answer. Okay? That's number one. Oh, by the way, can any of you here tell me, how do you know to stop?
When the residual value is small.
Right, when the residual error is small. So you can make that check, right? Okay? But the thing is, the residual, as you can see, is equal to factor B, factor B minus AX. I'm sorry, there's no more ink. Okay? The residual. Okay. Okay, the residual is equal to B minus AX. So when you calculate it, you get some number, right? In theory, each of these numbers is supposed to be 0, 0, 0, 0, then you stop. That is in theory. But in real life, you never get 0. So what you do, you just take the norm of this vector. Take the norm of this vector. Okay? Do you understand the norm? Let me give you an example. Suppose the residual vector is equal to, let's say, 0.3 minus 0.4. Suppose. What is the norm of the vector R? It will be equal to the square root of 0.3 squared plus negative 0.4 squared. Right? That will give you the norm. And this will be a number. Do you understand? So my point is, after you calculate this residual vector, you will calculate the norm. And you get only one number. And if that number is close to 0, that is enough to stop. Do you understand? So like for example, you say, you define epsilon is, let's say, 10 to the power minus 6. What is epsilon? This is called error tolerant. Error tolerant. Ten to the power minus 6 is a small number, right? It is not 0. This is a small number. So, right after you calculate the residual error, you will calculate the norm. And then you say, if the norm of the error is less than this value, then you stop. Okay? So now you can see how many iterations it will take in order to get the converged correct solution. It depends on two things. What are they? How many iterations it converts depend on two things. What are they? It depending on what is this value that you provide. If you provide very small number here, it will take more iteration. Okay, that's number one. What is the second thing? The second thing